Greetings. Just continuing on the subject of the different types of testing ideas and picking up on the list, there's a few that I'm going to cover a little less deeply, but each one of them does have some description in the book, Charting the Course, Coming Up with Great Test Ideas Just in Time, so you can get richer collection of ideas about these. But I want to go through them and make sure that they're covered. And these types of testing ideas here, from here to the end, might not apply on every single project. The first bunch that we went through definitely apply broadly to a lot of different software projects. Take state models. State models are useful for designing objects in software engineering and electrical engineering, probably in chemistry too, in a lot of fields of endeavor of mankind. State models are images drawn to represent the stateful nature of a system. Usually they're drawn with circles or ellipses, which represents the states of an object, and with arrows or lines, edges, if you will, to represent the transition between states. So a stateful system can be very formal. There's a language called the Unified Modeling Language, which allows you to define pretty strict states, and there's all sorts of symbols and mechanisms to do that. Or they could be rather informal, capturing the states that you observe. You draw a circle, you move to a new state, you draw another circle, and then you sort of try to figure out what causes the transitions, and you put the lines for that. But it is almost always helpful, if you have a stateful system, to model that stateful system, to draw some sort of diagram, to visualize it. Anytime you, by the way, have a diagram like this, it can also be represented in a tabular form, right? So you can have a table with one column for the initial state, one column for the ending state, one column for the transaction, one column for the variable output, all this type of stuff. This little diagram here represents the state model for a coffee machine. A coffee machine is very often an embedded software system, and to get a handle on how it operates, drawing a state model might make a lot of sense. So the device is powered down, it's in some sort of a null state, then we power it up and it goes to an idle state. Now an idle state is sort of waiting for an event, waiting for something to happen. If you start putting coins into it, it goes into the inserting coins state. And it keeps in the inserting coins state until you enter the right amount, and then it goes to a choose some sort of coffee state. Once you're in the user choose state, if you find a type of coffee you like, you press the button, it goes into the make the coffee state. If you're in the user choose state and you sort of say, no, sorry, I want to cancel the transaction, it'll give you your money back and put you back in the idle state, or so it should. And then if you're in the make coffee state, once you take out the coffee that was made, it goes back to the idle state. And if something jams or mucks up or goes wrong with the process, the device may go to a service state. And when the service is done and is resolved, it gets reset to the initial condition. It goes back to an idle state. So it's a model here that is not every possible state of this device, but it's a reasonable view of the device. And if you wanted to therefore use this to come up with test ideas, if you had a state model, you could basically say, okay, let me try to identify a series of tests that exercise each state at least once. And maybe you want to find out, can I get to each state? So can I get to each state? That's an interesting test idea. Can I exercise each transition at least once? Can I try to trigger a transition that's not supposed to happen? So this is a type of failure mode type of test. Try something, try to trigger transactions that aren't supposed to happen. And then there's the pathways through the system. So what are a reasonable subset of the pathways? Sometimes you can enumerate all of the pathways. In this system, the paths that might be interesting is idle, insert, coin return, idle. So that's sort of path there. Then there's a path down here where you have idle, insert coins, user choice, idle. Another path, idle, insert, user choice, make, idle. Another path, idle, user insert, user choice, make, service, idle, etc. So you can identify a bunch of paths through the system, and then you can say, okay, let's exercise each path at least once, or let's exercise each path with different types of data at least once. So you have a notion of coming up with test ideas from a state model. And if you're able to describe the behavior of your system with state models, you may actually be able to follow a type of testing that people call model-based testing, where you basically write a program to traverse the model and control the application and see if the state of the application matches the state of the model. You do that with things like finite state automaton and things like that. A lot of researchers like to study model-based testing. So it all starts with, can we create a state model? Now, a lot of non-technical people have a great deal of difficulty identifying what is a state. Jerry Weinberg, in his book, Requirements, Quality Before Design, he basically suggests that a state is a situation which we can recognize if it happens again. I sort of love that sort of simplistic model of what is a state. So a state diagram is, by the way, usually done with what's called mathematically a directed graph. If you can create a directed graph, you can always do analysis of the pathways through a directed graph. So not just state modeling, but any type of testing, if you can draw a directed graph, you can start driving test cases from that if you're so inclined. So that's state model testing ideas. It's great if you have a stateful system, handy in embedded software, handy in transactional software. We see the states of a transactions. For example, if you're applying for insurance, you might have an application, the insurance is applied for, then you might have, that's one state, then it might be approved, that's a second state, then it might be active, that's a third state, and then it might be continually paid for, it's a fourth state, and it might be canceled, that's a fifth state. So these are the states of a transaction, and as the life of the transaction goes on, events may cause the state to change. So that's the state model-based test ideas. We looked at many types of test ideas, and all of them relate to the user using the system to do something. Sometimes we can come up with test ideas by looking at data. And data-centric test ideas are dominant in some types of software, especially financial and transactional software where money is involved. There is a lot of places data goes to. Logistics software, the software that's driving a lot of our economy today, is moving goods around. So the whole logistics world around there involves really a lot of motion of data. If you take a look at Amazon, Amazon is all about data. So we have data. When we have a data-centric universe, data might be a source of testing ideas. I have customers who, when you start analyzing the work they do technically related to testing, you see it gets up to about 80% of stuff related to data in some sectors. So it's an amazingly important thing in some environments. So with data, you might start saying, okay, let's look at flow. Let's look at like where data came from, where data is going to, are there different pathways data takes through the system? And we want to maybe exercise all the different paths that data flows through the system. That would be called data flow test ideas. You look at the path the data takes and you simulate that path. You try that path out. Then there's test ideas that might come from the structure of data. If you have a database, take a look at the schema, look at how it's organized, and see ways to exercise the structure. Maybe there are a lot of different types of objects that are in there, and you can sort of figure out ways to build them, to classify them, to organize them, to exercise them, to manipulate them. We can use the structure to help guide us in constructing data. Some companies do this by studying patterns in data, realistic patterns in data, and then try to replicate them in test labs. So this is data structure. Now, the structure of data and the values of data are interesting things. Sometimes you're not allowed to have real data. Medical software, for example, doesn't really allow testing people or developers access to real data. It's confidential unless the actual customer, the end user, the actual end user patient gives you permission. So we may want to simulate the data. So we might take data and create fake data which has similar patterns, similar statistical properties, similar organizational properties, similar structures to the actual commercial data. There's also a possibility we may want to obfuscate data. That means we want to take a real data and hide anything that gives away private information in that. like obscure the names, obscure IDs, obscure phone numbers, so that it's basically not possible to reverse engineer it. This is obfuscating data. You may also want to sample data, look at data different ways. There's all sorts of interesting data-centric views, how to collect and build data. We can also look at data and say, well, where does it come from? And simulate the creation of it. Data can be changed, so simulate changing it, updating it, deleting it, removing it, resetting it to controlled states, and some of my favorites, backing up and restoring data, and also migrating data from one version of software to another. These are all interesting things that happen with data that may well be worth exercising in your software project. This is a source of testing idea. Basically, it's not here, follow the money, it's follow the data. So follow the data might give you some excellent testing ideas. And this is not looking at the functionality of the application, it's looking at actually the data in the system. And then there's, of course, test ideas that derive from the environment. Now, you remember we talked about the depth of testing and how environment has a relation to that. So I like to suggest that on some systems, there is an environment risk that's very significant. Different versions of hardware, the application may behave very differently. Different versions of software, different operating systems, different operating environments. The application may behave very different in the world of iOS and in the world of Linux and in the world of Windows and other operating environments. There's tons of them. There's locales, which is language or cultural specific variants of the operating system. And this is, of course, today, the world is huge, but it's all connected. And so we're all interacting as if we were across the street from each other. It's intriguing how McGill, for example, trying to do virtual stuff, is actually got people in classes from all over the world right now. It's quite distributed. People are working in different locales. In different locales, there's different things people do. There's different, for example, collating sequence. How do you sort data in Montreal if it includes French data? How do you sort multilingual French data, English-French data? How do you sort French data in France versus in Quebec? There's different collating sequences and collating approaches. There's things like interweaving masculine and feminine street names or saints in lists of things. And it's not following the alphabetic collating approach that you might be used to in English. So there's all manners of different variations in the locale that may make your application behave very, very differently. As well, there's different business rules and different tax structures, different data entry techniques. There's all manners of things. I know that when I look at localized software, I always had a fun time with languages like, for example, some of the Germanic languages or some of the Scandinavian languages, which use compound nouns. And so you have suddenly you have these big long nouns that have to fit in fields that in North American systems, normally 10 or 12 characters would be enough. Now you need to consider, wait a sec, that might require 30 to 60 characters for the same field. And it really would look choppy if you sort of tried to look at that same data on a system in Germanic speaking locales. Then we have environmental stuff like how are we interfacing the device? I know there's different mobile devices, but also different browsers, different plugins, different versions of different browsers and different plugins. This list, if you look at the combinatorics, is ridiculous. It explodes quite a bit. So it's important to have strategies, and the strategies have to blend with business risk, because you want to be confident that the browsers or the environments that your end users are going to use will behave consistent with your desires. And also you want to make sure that the things that are a little out of date still don't cause problems, and things that are maybe not supported, you don't want to get accidentally get security risks and stuff like that. So this is very important to have a strategy that ties business needs to technical risks. Luckily, today there's also services that allow us to do platform compatibility testing. And in one weekend, for example, you may be able to test your software using a service on multiple tens of thousands of different environments. There's also robotized labs that do this on mobile devices, for example. Amazon has one, but many companies have these labs where you basically provide scripting to guide software which controls robots, which actually walk through your app, following, like simulating all of the keystrokes and navigation techniques, etc. So this is basically, you can do this on tons and tons and tons of different devices, and each device can be configured with different options, different software, different locales. I always like to emphasize the fact that other software running at the same time as yours presents an important environmental risk. Code-dependent software, other software running on the system at the same time. I know it's not even written by you. It's from another company in another place. And I know if it's got a bug or a problem in it, it's probably not you who's going to be able to fix it. However, if that software is sharing resources with your software, there may be interference. And for sure, there's going to be a performance hit if there's two applications fighting for the same CPU resources. But there's other resources that may also be challenged. I've seen cases where databases are being the resource that everybody's after at the same time, and you really run into standoffs where both applications are waiting for the other application to liberate the resource before they continue. And these standoffs look like really terrible bugs in the software from a user experience point of view. And when you did all your testing or all your development in your lab, if you never tried third-party co-resident software sharing common resources, you probably will have no idea about it. And your support people may have a very hard time helping the customer. So there's a concern about how your application might behave with third-party co-resident software. And by the way, there's also nice combinatoric test design techniques, which can help us come up with very meaningful test environments to shake this down, to try to find it in a controlled lab. Test ideas. So we talked about test ideas from the point of view of functionality. We talked then and said, well, maybe data, maybe environment. Well, maybe we could actually look at the code, talk to the programmer, look at what's going on in there, take the code, critically review it from the point of view of technical risk. What can go wrong in that code? Now, there's, of course, static techniques to study the code to try to find actual defects in the code, which is cool. I think that's really neat. And in some programming languages, especially legacy programming languages like C, C++, there are constructs in those languages that really, really make it easy to trick the environment into doing things that are not healthy. There's a thing in C called casting. And casting dates back to the earliest days of the C programming language, when the people at Bell Labs really had no memory and very little CPU resources, and they had to implement some pretty fancy, complex algorithms. And so what they would do is, well, if they had a pointer or they had an index to a structure that had less than 255 entries in it, they would sometimes say, hey, let's just take a byte, and instead of storing a car in it, let's store a short integer, a really short integer. And even that, they would say, let's put a positive integer, not a signed integer. So there's all these tricks people would use to get down that 8 bits to be used as a pointer. And then they'd write really efficient code, which would auto-increment these pointers and whip through arrays really quickly. And it was white lightning and great for embedded software or kernel software in operating systems. Of course, the trouble is that if that array ever extended beyond the size of 1 byte, pointers with 256 or what have you, then you start referencing code that is sort of not the code you intended, because your byte only goes up to 255. After that, you add 1 to it, it goes back around and wraps around. And so we have basically all sorts of problems with accidentally corrupting inappropriate memory or accessing memory wrong. There's just super risks with this whole notion of casting. And of course, casting was all sorts of types, could be cast into other types for optimization and manipulation. This old legacy code is still around, it still runs, it's still pretty efficient, and the casting stuff still works, but it's a risk. So static analysis tools can help you find that type of stuff, So we can actually find defects, right, by looking at the code with static analysis tools. It's not just hints to improve the maintainability, which is what a lot of static analysis tools promise to do, to help you reduce the maintainability costs of your code, but they can actually find bugs in your code, which is pretty cool. They can also find bugs in things like semaphores, record locking, multi-threading, stuff like that. So we have, is your code thread safe is an interesting thing. But the white box testing, for me, it's just fantastic to look at the actual technical solution. How are the programmers solving the problem? And then looking in there for weaknesses or for elements of the solution that suggest ways to test things. You can also look at the code to come up with what I call black box test ideas to test the system from the outside, but you can also come up with the test ideas based on things like coverage models. So you might look at the code and say, okay, I would like to come up with a set of tests that exercise all the code, or I would like to come up with a set of tests that exercise all the decision outcomes of the code, or I would like to come up with a set of tests that exercise all the conditions that lead to decision outcomes in the code, or I want to test all of the paths or all of the basis paths, or if I could turn this code into a directed graph, I might want to write a set of tests that exercise every edge in that graph at least once, or every node in that graph at least once. So these are all models that once you have the code, you can use to sort of say, okay, let me construct tests around these models. And some of these type of tests give people confidence that we have a strong structure, but those tests are always risky because when you're looking at the code, you're looking at the solution, right? You're not looking at the problem. This is white box. You're looking at what the programmers wrote. You're testing what they wrote. Unfortunately, when you look at bug fixes, and there's been a lot of work done by Boris Beiser and other people in history of software studying what programmers really do when they fix bugs. I certainly did several interviews on this over the last several years, and it's not a very hard research project to just talk to programmers and say, please explain to me, what did you do to fix this bug? What did you do to fix that bug? You start listening to this, you build a little catalog of what programmers did. Almost always, the programmers had to add code that wasn't there, or add a condition that wasn't there, or manage data that wasn't there. There's always some omission that gets plugged by adding something. So the point I'm making here is, if whenever a programmer fixes a bug, or often when a programmer fixes a bug, it's adding something that wasn't there, how could you possibly have covered that in your testing? You cannot cover the code that's not there. So white box test ideas are very challenging when it comes to trying to identify a bug of omission. At the very best, what you're going to do is gain confidence in whether your testing covers what's there. You may be able to identify things in your code that are not tested. So that's nice. That's interesting to say, hey, wait a sec, we studied our code and we have no tests for this chunk of code here. That's an interesting thing. For me, that's very intriguing. However, you will never really find a bug of omission. You can't design a test for the code that someone forgot to write using a white box technique. So that's white box ideas. Bug taxonomies ideas. This is where you look at collections of bugs that could have happened on similar systems to yours. People have been collecting bugs this way for a long time. One of the first ones that I know of was Dr. Ken Kainer. Appendix A of his book, Testing Computer Software, has, I believe he calls it 400 common software bugs. This book was originally published in the early 1990s, late 1980s, and that list is still relevant. So there's I believe I put a copy of that, or I will be putting a copy of that in the Dropbox. Boris Beiser, who was a champion of testing as a role in software engineering. Boris Beiser wrote the very famous book, Black Box Testing. He's also a champion of computer architecture and performance analysis. He collected bugs by interviewing programmers about what they did to fix them. And his catalog is a taxonomy of basically what can go wrong in software, what type of things technically can go wrong in software. His work, he ended that somewhere in the early 2000s. A gentleman from, where was it? It was the Benelux countries. Otto Winter took over the work from Boris and continued adding to it. I caught up with Otto Winter sometime in the late 2010s, and Otto Winter shared with me the list at the time, and he had remarked that he had only found a few new types of bugs, even though he had interviewed several dozens of programmers. And this list, of course, is a big classification scheme with lots of bugs. And if you start looking and saying, well, wow, the technology has dramatically changed in the last 20 years, and yet you only found a couple of new types of bugs. And it basically leads him to the conclusion, and I don't know if this is always going to be true, but from the studies of Boris Weiser and Otto Winter, it almost is clear that programmers have perfected injecting bugs in code. It's like they're not coming up with new ways to do it. This is both encouraging and discouraging. The discouraging part is great. We're making the same errors over and over again. Shouldn't we learn how to avoid them? And the answer is we should learn how, and we're probably going to have better luck in the future with new technologies that don't make some of these problems possible. But on the other side, and this is a great thing, because by studying these taxonomies, we can sort of anticipate what type of problems there might be in software systems. So Weiser's list is an interesting one to look at to say what could have gone wrong in the programming of the system. And for me, that's an interesting source of ideas. There's 2 or 3 taxonomies published by graduate students of Dr. Ken Kainer when he was professor at Florida Institute of Technology, FIT, and they were to build taxonomies. So one was by Jiri. It was a taxonomy of transactional problems with shopping cart applications, hundreds of pages of bugs, all of them real bugs that really happened on real systems. And there's another taxonomy published in a very similar vein about mobile bugs, cataloging, again, hundreds of pages of bugs about mobile failures, applications, real ones, real problems in the field that happened on mobile applications. So these collections of bugs are basically specific to a sort of solution space, but they're beautiful because all of the bugs happened on real commercial systems. You can't argue with it. They're well referenced, cross-referenced. You have all the information there. And there's other taxonomies. I leave you to hunt down some. People create their own if they can build catalogs of problems your customers have had in the field, or bug lists from your projects, and you aggregate them to sort of put it into a catalog form. If you have a taxonomy, there's a lot of different things you can do. I've got some professional colleagues that like to, for a programmer, look at taxonomies and build a checklist of programming practices. Maybe they're going to look at the top 10 list of programming practices based on stuff they have from a taxonomy. So you're not looking at like 1,000 entries in the taxonomy. You're just looking at, hey, what are the top ones that we think are really important for us in our context on our project? And then there's that's building a checklist, not a bad idea. I like to use them just to basically help me, what I say is salt and pepper my project and come up with new test ideas to help me with my creative thinking. So what I'll do is I'll take a taxonomy and I'll basically open it randomly to a page, or I'll come up with a random number which indicates what the page number is. And then I'll read that page and I will discover that that page has a description somewhere of a bug on it. And because they're collections of bugs. So I basically randomly go to a bug, read it, and I ask the question, I said, technically, could this bug happen in the system I'm testing? So could it happen? That's the first question. If it could happen, the second question I might ask is, would it matter? If this bug happened in our system, would we care? Is it something that we would never want to fix, or is it something that would have a lot of problems downstream? So we look at the bug. Could it happen? If it could happen, would we have to fix it? So that's the second question. And if the answer is yes to that second question, well, the third question I like to look at is saying, have any of the other test ideas that we've decided to implement, have any of the other tests we've decided to create, have any of the scripts that we've already got in our catalog here, would they have exposed to this problem? And if the answer is yes, then I can stop there too, because I've already got something about that bug. But if the answer is no, then I can basically come up with a test idea, which is to confirm or refute the hypothesis that that bug is actually in my system. And I would be able to design a test or an experiment to confirm or refute the hypothesis that that bug is in our system. And this is a bug. Now, the beautiful thing about this test idea is it did not come from a requirement. It did not come from a design. It did not come from anything except knowing what the behavior of similar systems might be. So it's like a test idea without the usual sort of source, without the usual place it comes from. It's lovely. For me, it complements my testing, and it brings up ideas that can happen. Most of these taxonomies are beautiful bugs that happened on real commercial systems that were live. I mean, these were live commercial systems. So, moving along, there are interesting test ideas when you start having multiple operations that can happen concurrently or in different orders. What I call across-story relationships. I use the term story just because the story that is a type of requirement where we model the user's interaction with the system to get some sort of a job done or task done by the user. If we're looking at that, we have multiple stories. If the stories involve shared resources, then they might interfere with each other. And this might lead to inconsistent behavior or risks if things are done out of order, or multi-threading resource contention problems. Is all sorts of interesting things that can go wrong. So when this test idea comes up is when you have multiple stories that share common resources or common processing or common data, and you basically study how they interact with each other. Think about this. Imagine you are at a company like Amazon.com, and you have one process, that's one story, if you will, which is the inventory story. And the inventory story says, well, when, I don't know, when a new book comes on the market, we add it to inventory, or it might be when we have a book is no longer for sale, we'll remove it from inventory, or when we have no inventory, we don't sell it, or something like that. So you're basically managing the inventory, managing what you can sell. And the other story is, I want to buy something. So I want to buy a book. So what if now the inventory management story changes the state of the inventory for the book that I'm trying to buy? So I'm buying a book and the inventory is being changed at the same time. If you think about that, you'll think there's possibility that the book at the beginning of your transaction is available, but at the end of the transaction is not available. What happened in the middle? Do these applications play well together? Do they use mechanisms like record locking to make sure that the database doesn't get manipulated by multiple people at the same time? Do they have semaphores to make sure you wait for some processing to finish before you continue so that you can do safe multi-threading? What mechanisms are put there to make it safe? And I love these type of test ideas. They lead to finding really important bugs, which if you just focus on testing one feature at a time, you may totally miss this type of problem. So across feature interference, when they come up, by the way, in agile teams usually is when a new story is being implemented. Then you sort of say, okay, what other stories use the same resources, the same code, the same data, etc. And then as part of the implementation of the story that's making the change, you'll exercise the related stories with it. And this might involve by things like stress testing, etc. A lot of people who test software for a living sort of have a lot of fun explaining to their neighbors what they do at work. You know, I've seen it many times. I've done it myself. You know, what's your job? Well, I get paid to break things, or I'm a software breaker. I get paid money to break software. I mean, what fun, right? It's sort of it's a LARP to say that. But software breaking is actually a type of testing idea. Now, people who test software don't really break it. Probably it's broken more by the person who programmed it than the person who's testing it. But software breaking is a nice metaphor. Sort of, you're saying, okay, how could I break? How could this break? Let's prove it. Or disprove it. So software breaking is really a term for a sort of very specialized type of failure mode testing, and it's built around the notion that we want to try to deliberately find weakness in it to challenge the robustness of the software. So we want to challenge the robustness of the software with software breaking. James Whittaker wrote 3 books about the subject of software breaking. He wrote a book called How to Break Software, How to Break Web Software, and How to Break Software Security. And then John Hagar, with permission of James Whittaker, took it to the next step, and he wrote a book on how to break mobile and embedded software. So we have now a catalog of 4 books that describe software breaking. And in software breaking, the approach as it's taught is you start by creating a fault model. They have, and these are things that you learn by studying the books and things. It's a lot of work to figure out how to do it, but you create a fault model, and it's sort of like the block diagrams I've already talked about. So you look at the fault model and try to identify in the fault model, is there areas of particular weakness that you want to explore or exploit? Then you look in these books, these references, these catalogs, and you find a specific attack. So each one of the books I mentioned has about 100 each of named attacks. That's about 400 named attacks that you can choose from. A classic you probably heard of is a denial of service attack, but there's also buffer overflow attacks. There's all sorts of CPU saturation attacks. There's all sorts of attacks depending on which one of the books you're reading and what type of attack, what type of software you're breaking. So you choose a relevant attack. It's an attack that's going to help you expose a weakness that matters to you. Don't start doing this for things that don't matter. Right? This is only for things that matter. And once you apply the attack, then you'll be able to say, is the application robust from the point of view of that attack? And so this attack, it may involve having to write some code. It may involve some sort of interesting testing or some use of tools. There's user interface attacks, system interface attacks, data interface attacks, security attacks, all manners of attacks. So the type of testing idea to challenge the robustness of your software is basically called software breaking. Another pretty common test idea is an end-to-end test. End-to-end test where you basically exercise the entire process change from inception to a completed transaction, including any automatic or manual steps in the process, including your service and third-party services, your systems and external systems that the transaction has to go through. So a nice end-to-end test is a good ending idea for confirming that, for example, a story has been implemented correctly, but it does require a lab and an environment that includes all of these elements. And unfortunately, during a lot of engineering, we will be forced to use what are called mock objects for third-party systems. In a true end-to-end test, we replace the mock object with the real object. So we try to basically go through the real chain that the software is going to be going through when it's in production. That's called end-to-end testing. Paths and sequences. So if you take a look at a bank, go into the bank. These days, I don't go very often to the bank, but when I do, I like to take a look at what all of the tellers are doing. I don't, just off the side of the corner of my eye, I'm not spying on them. I'm not trying to look really at the data, but I see that their screens are flipping from page to page to page to page to page. And sometimes it looks like they have a mainframe application, and sometimes it looks like they have a terminal emulator window, and sometimes it looks like they're doing a sort of fancy user interface, but they're moving around. And in one transaction, it's obvious that they've got several dozen screens that they're flipping between. And it's interesting to note that the development of these systems do not have prescribed workflow. What they do is they have a whole bunch of screens, and the teller basically goes through them in whatever order is required to get the transaction done, which means that you can actually probably move from any screen to any other screen just by knowing the right hotkey sequences. This means that through the network of screens, there is probably an infinite number of pathways through that network. And so testing ideas relating to sequences of operation loves that type of problem space, where you have sort of this large amount of possible paths to go from point A to point B, to go from starting a transaction to finishing a transaction. And we can't possibly test all of those paths And it could well be infinite. If there's looping, it is infinite. There's an infinite number of possible paths. So we want to try to say, okay, can we model the system? Can we model the workflow of the system with some sort of diagram? Usually I try to do it with a directed graph showing all the possible pathways, if you will, through a system. And then once I've got that diagram, then I will use certain algorithms to help me basically find a subset of those paths, which will yield very important knowledge to me, information to me when I'm testing. I know that I can't test all the paths, so what's a reasonable subset? And some people would describe the basis paths as a subset that's considered very reasonable. That's a subset that has, if you exercise the basis paths, you've exercised every step at least once, every branch at least once, and if you take the tests that you've done, the paths that you've done, you can make a linear, by linear combination. What I don't really know what linear combination mathematically rigorously means, but you can combine the paths that you've done to get any path through the system. And this is McCabe's theory of basis path analysis. So basically, this is sequences of operations where we're basically going to vary the paths and vary the way we walk through it. We may try valid things, invalid things. And then if you got something like this, you might try concurrency, multiple things at the same time. Sequences of operations, order of operations. You may well see this also in applications like calculators, for example, where you can have pretty much almost any key in any order. So that's sequences or sequence of operations testing ideas. Leads to a lot of path analysis. Business rules. Business rules. Business rules in some domains are considered assets of the business. A business rule is an asset of the business. It's how people make decisions. It's how you decide how much money to charge for an insurance policy. It's what a bank uses to figure out how much interest to pay on a term deposit. It's what the government uses to figure out how much tax to charge someone. Every domain, every business has its own rules. And these rules get encapsulated in software. And once you have them, it becomes really, really, really important to exercise these rules, to say, are these rules valid? Have we thoroughly tested them? So what we might do is we might say, can we build a model of the decisions? And then can we exercise a reasonable set of tests to be confident that the decisions are all covered nicely and in a healthy way? And sometimes people take terrible risks in this domain because they're not sure of how logic systems work. Luckily, people who are students of software engineering or computer science take courses in logic and logic design, and they can understand Boolean algebra and stuff like that. But if you don't know Boolean algebra, sometimes this is very perplexing to come up with the tests for the business rules. There's limits, constraints, so things that are up until this point we do it. So what's the limit? Well, I don't know. You're going to get no tax until you hit $23,000. Then from $23,000 for the next $8,000, we're going to tax you at a low rate. Then we'll tax you at a high rate. And if you get over this much money, we'll tax you at an absurd rate. So you have the notion here of different limits, different behavior. There's constraints, what's in, what's out, what's allowed, what's not allowed. Certainly, we've seen this in certain systems where if you get one thing, you can't get another. So you can get a discount because of your age, you can get a discount because the product is on sale, but we can't combine the age discount with the sale discount. You only get one. Take the one that's more advantageous for you, but you only get one. So these are limitations and constraints. Business rules can be deterministic of the way that you implement business processes. They can also be things like saying, hey, who has to authenticate something? You know, if the amount of an expense is less than $5,000 plus tax, an engineer can approve it without going to his manager. But if it's between $5,000 and $25,000, the engineer and his manager must approve it. And if it's over $25,000, it's got to go up to the VP of the organization, et cetera. So that sort of process models would have really cool business rules about authenticating and approval of processes. Transaction logic. This one I love to look at. The example of transaction logic for me has to be the shipping cost calculations for Amazon.com, which is interesting because it cares, is it Amazon? Is it Amazon Prime? Is it Amazon ourselves, or is it a third-party vendor? And all of these things weigh in with the amount of items in the shopping cart and the amount of value of them, and then probably even the size and shipping type. And there's really complex decision tables for that. Postal rate calculators also full of those type of things. Insurance domain full of those type of things. A lot of different transaction logic in there. Business rules are really value to the company, and sometimes they're trade secrets. They're great trade secrets. One company will not share their business rules with another one. If you look at financial companies, how do they determine how much dividend to pay their shareholders? Probably those algorithms, those rules around that are well-guarded secrets. You don't want people to know about that type of stuff outside of a select few. So business rules, very important part of testing. I would say that, in fact, if you're in the financial services industry, it's key, because the business rules are not just logic in software, it's value to business. And it's a competitive advantage too. One insurance's business rules are more clever than another, they're going to make more money on the business. There's test ideas just with the world of combinations, right? As soon as you have multiple variables and each variable has multiple options, you start looking at how many possible combinations, how many possible permutations there are, and these numbers explode. They just grow so big, so fast, it's outrageous. I always share examples where in a system, the customer had 60 factorial tests they thought they would try, and 60 factorial is 8 point something times 10 to the 81. You have a number that's so large, it's bigger than the number of particles of atoms in the visible universe. There's no way we could test that. Not with all the automation in the world, we couldn't test that reasonably. So combinatorics is something that's critical. Understanding the permutations, commutations, selection, the algebra, the calculations around that, how many choices here, how many choices there, will guide you a lot in understanding the size and complexity of your testing problem. Now, we can always do, the first step in combinations is to figure out what's a reasonable set of variables. And we don't have to vary everything. So we can say, okay, let's vary the ones that we think have a risk of interfering with the behavior of the software. Then we can choose selections. We don't have to have every option for every variable. We may say, let's vary the most common ones. Let's not interact with invalid ones, etc. So combinations test ideas basically just look at the universe and say, okay, can I get a reasonable subset of all of the combinations of possible things that could happen that will give me insights into what the behavior of the system is? One model that's really graceful in this area is called Pareto analysis, where Pareto's an Italian economist who basically discovered that what was the 80-20 rule, right? That 20% of the transactions happen 80% of the time. The economic theory was that 80% of the wealth is in the hands of 20% of the people. So if you have a transactional system and you know what the 20% of frequent transactions are, or if you have historic knowledge of how different variables are changed across transactions, you may well be able to find a Pareto sweet spot and then test those. So that's a valid subset. That's basically going to give you insights, knowledge, a warm, fuzzy feeling, perhaps, of comfort that normal things work normally. However, you are not going to find what we call black swan events, where you're not going to find outliers, which are sometimes catastrophic combinations of things. So there's other techniques of test design, for example, pairwise test design, whereas if you have n variables, you choose 2 variables, and you make sure that for any 2 you choose of the n, that you have every possible combination at least once. That's pairwise. If you have a pairwise complete set, you will have a lot less than the total number of combinations possible, but you will really, really thoroughly exercise the system, because I have taken any 2 variables and exercised every combination at least once. So this pairwise complete set becomes a pretty strong combinatoric test for environments where we can't try them all. It's a reasonable subset. So Pareto is modeled after usage. Pairwise is modeled after sort of combinations. Both of them may be perfect on a specific project. And there's other techniques as well, which we'll look at when we go into a little more depth on test design. But any serious testing project always runs into these combinatoric problems. There's an explosion of possibilities. Bunch of test ideas can come from the universe of internationalization and localization. I get a kick out of some of these type of test ideas, because it's if you're used to writing software just for your own locale, then you sort of get shocked the first time. You say, oh my God, I got to get the software running around the world. And there's so many issues: language, culture, GUI, the graphical user interface. There's, there's only that many pixels, and I got to get all those characters from all those languages in there. How do I do that? And do I have to have people who know all these different languages to help me to manage and process them? What about searching, sorting, collating, just testing the code in all these different environments? It becomes horrific. However, the projects that are going to be targeted to multiple locales are often broken into two parts. The first part is internationalization, in which we enable localization. And so what some people will do is a fake localization into a fictitious language. Like Harry Robinson published something called Testing in Klingon. The idea is you create a fictitious language, which is sort of self-testing. So the localization is not really a translation, but you might take the words, for example, and permute them, or not permute them, but reverse them. Or you might double every letter and reverse them. And then that's a weird thing, right? But if you localize into that, then by reading the screens, you can tell if it's correctly reversed without knowing anything about the linguistic nature. So we can test an internationalization without doing the localization. And if we find the bugs at the internationalization time, which is enabling the localization, then we can fix that before we start worrying about language specific stuff. So the idea is to try to find internationalization bugs first, fix those, get rid of those, and then worrying about localization. And there's cultural reasons why it might make a lot of sense to do as much as possible what they call in context or in country testing for the localization, simply because in the locale, they're using co-resident environments that have all the elements of the locale. And frankly, people or organizations like Microsoft have over the years done great work by doing that. And today, with distributed computing as clean as it is, I think it just makes a lot of sense to do in-country localization testing. And this is not just testing the translation, it's testing local specific searching, rules, businesses, currency, number formats, etc. And also multi-byte languages, right-to-left languages, etc. Other types of testing ideas. Well, when we looked at the testimonial, we saw that unit testing is a type of testing that's done when a programmer is ensuring that the chunk of code they're working on is okay. So unit testing is a source of testing ideas, if you will. How do I know I'm done programming the code? It would be looking at things like the structure of the code, the data in the code, any coverage algorithms that we've got that we really want to conform to. And we want to make sure that the code follows from the design follows from the requirements, and they're consistent with each other. So some people will look carefully at the unit testing to come up with test ideas. What I urge Agile teams to do is, before you start programming a story, whatever story you've decided to do, to have a short session, and I would suggest a maximum of 30 minutes for this, and literally brainstorm unit test ideas, and have some people who are not necessarily programmers involved in helping to do that. If you do that, then it'll be a lot easier to practice some interesting methods like test-driven development, where you create the unit test before you create the code that implements the test that's going to be exercised. Test-driven, you write the test first, then you write the code. You just write enough code to pass the failing tests, etc. It becomes an interesting agile approach to programming. Sometimes we don't really have a lot of knowledge about what the requirements of a system are, but we have a lot of knowledge about how to assess correctness. So we have knowledge of how you can tell it's right. if we have knowledge of correctness, if we have what are called testing oracles, which are strategies to assess correctness, well, that may help you come up with test ideas. So if you know how to tell the answer is correct, that might drive what is a test. So let's apply this method. Let's apply this approach. Let's apply this program. For example, if you have a new program that's being released and it's replacing an old program, well, it's sort of obvious to do some sort of side-by-side testing of the old program versus the new program. So the test idea would be to do the side-by-side testing. You know that because you have that as a strategy to assess correctness. So assessing correctness can be done a lot of different ways. You can have just known truth. So we might say, hey, here's the laws of physics. We're going to test every law to make sure it still applies after we write our software. So an object in motion is still in motion. Okay, we're done. Gravity, good, we're done. Equal opposite reactions, excellent, we're done. So we have a list of things that are known to be truthful in whatever the domain is. We might have requirements which indicate what the truth is. So we can basically say, okay, if this requirement must be true, then we can have a test to confirm that that requirement is true. We might have a state machine that's a model driven, that says this is the behavior of the system. If you look at a test oracle like a state machine, one of the beautiful classic examples was when when Google Maps was tested, they created a state machine which basically would generate the pathway between point A and point B, and then they would basically compute the distance between it and see how that distance varied against the Euclidean distance, and they would compare the two, and if there was too big a variation, then they would flag that as a problem and have a human being take a look at it. It's awesome state machines that went on for literally months, running thousands and thousands and thousands of test cases. Subject matter experts. Interview a subject matter expert. You probably learn a lot of different ways to test the application from the point of view of the domain. Again, just like requirements, the design might give us points to observe the application, points to control the application. We might have rules of thumb that we can get from people who are practitioners in the domain, or we may have a mechanism or tool that can help us validate things. Whatever our test oracle is, it itself could be a source of testing ideas. So if you do have strategies to assess correctness, use them. That gives you a bunch of test ideas. One of the interesting things about software engineering is we have lots and lots and lots of boundary bugs. Boundary bugs. Why do we have so many boundary bugs? I don't know. Frankly, in the 1990s, I was of a school of thought that said that if we improve our requirements and disambiguate them, we'll be able to avoid or almost eliminate boundary bugs. But still today, we have excellent requirements that are not ambiguous, but we still have boundaries and boundary problems. Somehow I think it's just when you have multiple people working on a project that it's easy to misinterpret even if it's unambiguous. So boundary tests, and there's a wide range of what is a boundary, but a boundary is a point where the behavior should change. So it could be a value range. So the extreme values of boundary ranges. It could be, I don't know, what's it, points where the behaviors change. Like if you look at temperature, so below 0 Celsius, it freezes. Above 100 Celsius, it boils. At absolute 0, it ceases to get lower. There's things about temperature that are basically where the behavior, the chemical behavior changes, like water changes, other things change around it. So the points that behavior changes, those are boundaries. And a lot of software systems have points where the behavior changes. There's systems that, for example, do load balancing. And if you have so many transactions per hour, they sort of throw in extra servers and stuff like that and distribute them across different processing. And then when the load gets down, they reduce the number of servers. And this is interesting because those are points where that point is an interesting boundary. When it increases and decreases it, do we lose transactions? Did something weird happen? So time, security, all these things have boundaries. In the test case design section of the course, I'll probably be able to itemize dozens and dozens of types of boundary tests. The point is, if there is a range of values, it's probably a good idea to exercise the extremes. Not only the extremes, mind you. Automation. Sometimes we're fortunate to have a tool which can automate or mechanize a part of our software testing, especially repetitive operations or hard to observe outcomes, things that are like your eye can't catch it, but a piece of software can measure something like how many milliseconds did that operation actually take. Maybe we have really complicated computations and prone to human error, or just the fact that there's a lot of things going on. Maybe data is so vast and you want to compare it really, really accurately. So you basically want to use tools for it. So if I have automation tools, automation expertise available to me, I may, if it's relevant, it still has to be relevant to the purpose of the project, but I may come up with test ideas saying, let's use this tool for this purpose. We have this tool, here's a purpose, it can help us learn about risks on the project. So automation, if we have it, might be a source of testing ideas. Now, automation is also possibly a source of implementing tests, but I'm looking at it here saying, if I have a bunch of tools, could using these tools help us with this project? So this is a source of testing ideas. And probably the last one in this list is regression. So regression testing is a huge concern. Regression testing is something that's usually integrated with a continuous integration server, and it's very often automated. And what we're going to do is we're going to basically repeat testing over and over again for different reasons. We might do a smoke test, basic 1 or 2 transactions with normal data to check, is the software ready to be tested? Is it got build integrity? And we might also do a smoke test to say, is the environment ready to be tested in? So that's like a smoke test. Release readiness, is the release ready to go? Story tests, we might take every single or many of our transactional story tests, run them over in each build to make sure that they still pass the acceptance criteria that was prescribed to the requirements. And we might take every single unit test we've ever done and repeat them over and over again. And there are companies that do this. They literally run hundreds of thousands of unit tests and tens of thousands of story tests on each and every build. And regression is sort of interesting. When I look at implementing testing, I want to say, is something graceful to regress? Is there some strategy we can put in there? Can we, for example, for every operation a user can trigger, can we do that through some sort of hook? Can we do that through some sort of API? Is there a programmatic way to do it? Similarly, if there's states of the system, that can we observe it from the outside? So can we sort of pull it from a JSON object or something like that? So I want to be able to sort of say, can we observe and control things and put in the hook and maybe the instrumentation to facilitate regression testing? So that's where we're going to stop this section. I thank you very much.